So, welcome again to the new lecture of the course properties of materials. So, let us just briefly recap the last lecture. So, in the last lecture we looked at transformation of axis. So, basically you have one set of orthogonal axis, let us say I, j, k, and you want to transform to, or you want to transform from let us say another axis which is m and p. So, and for example, for stress one can use this relation sigma ij is equal to summation over n is equal to 1 to 3, summation over m is equal to 1 to 3, L I m L j n sigma m n. So, this is essentially and where L's are the cosines of angle between I and m axis and j and n axis, and sigma m n is basically depending upon the how do you add these. So, essentially we and this is also applicable for strain as we will see later on, and you can write this in general form by not writing this summation, but it is implied that summation is there, and so we wrote, you can write any one. So, you can write sigma 1 1, you can write expression for sigma 1 2, sigma 1 3 and so on and so forth. And I would suggest you very strongly to do this exercise at home, because and we give some certain examples of sigma x xx and sigma x prime, sigma x prime, y prime and so on and so forth, and then you can modify them a little bit by using the symmetry of tensors, stress tensors, that is sigma ij is equal to sigma ji, and then you can shorten it. And then we were looking at the concept of principal stresses. So, principal stresses and principal axis. So, principal stress axis if we define as 1 2 3, then principal stresses become sigma 1, sigma 2 and sigma 3, and this is what we were doing. So, let us take this further. So, one can define a relation between the principal stress values, that is sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 is equal to 0, and we wrote that these i's are nothing but stress invariants. So, I1 for instance one can write as sigma xx plus sigma yy plus sigma zz. I2 would be sigma yz square plus sigma zx square plus sigma xy square minus sigma yy sigma zz minus sigma zz sigma xx minus sigma xx sigma yy, and I3 will be equal to sigma x sigma yy sigma zz plus 2 sigma yz sigma zx sigma xy minus sigma xx sigma zx square, sorry, sigma xx sigma zy square minus sigma yy into sigma zx square minus sigma zz sigma xy square. Okay, and this is where we were, and so this basically I1 is nothing but essentially sum of these three principal stress, some of these three normal stresses, sigma xx, sigma yy and sigma 3 and I2 is this and I3 is this. And in terms of principal stresses, hence one can write these as so we can write I1 as sigma 1 plus sigma 2 plus sigma 3, okay, and I2 can be written as minus of sigma 2 2 sigma 3 3 minus of sigma 3 3 into sigma 1 1 minus of sigma 1 1 into sigma 2 2, and I3 can be written as sigma 1 1 into sigma 2 2 into sigma 3 3 is the expression in terms of principal stresses. So, this is a way to write the principal stresses. So, let us do a solved example for instance. So, if you take a problem, so this will become little clearer when you want to. So, let us first take the problem of the calculation of shear stresses on other axes. Okay. So, what we have looked at basically, we first looked at the transformation and then we looked at the expression for principal stresses with stress variants inbuilt in them, and then from these stress variants one can calculate what are the values of principal stresses, and that is what we are going to do now. So, let us assume there is a bar which is under a force along this axis, and let us say this axis is 210 crystallographic axis. Now, materials deform by a process, as we will see later on, called a slip on planes where, okay, so let us not invoke the phenomena of resolved shear stress, but on certain planes, okay, on certain planes on which atoms can move easily. So, this direction along which the planes are, let us say it is a 111 plane. So, 111 plane in a cubic system will have a normal which is 111 perpendicular to the plane, and the direction along which the atoms will move during deformation is the direction that lies within the plane, and this is 101 type of direction, and since it lies in 111 plane, the dot product of this direction with respect to plane should be equal to 0. As a result, this direction happens to be 10 bar 1 direction. So, basically we can say there is a, so although the normal stress is applied along 210 axis, the shear stress is on 111 plane and along 10 bar 1 direction. Okay. So, let us say we define 210 as M axis, 10 bar 1 as N, and 111 as P. Okay. If these are three conventions we follow, then we can write the expression for tau NP. Tau NP is the shear stress within along this direction 101 and in 111 plane. Okay. So, if we now write the expression for this happens to be LPM multiplied by LNM into sigma MM. LPM is basically angle between P and M, that is angle between 210 and 111, and this is the angle between N and M, that is the angle between 210 and, so cos of angle between 210 and 10 bar 1. Okay. And sigma mm is the stress that is applied, and let us say this stress works out to be roughly, let us say 3 megapascal. Okay. Okay. So, this is the 3 megapascal stress that is along the M direction, and so what is the angle between 210 and 111? So, that is nothing but 2 into 1 plus 1 into 1 plus 0 into 1 divided by square root of 2 square plus 1 square plus 0 multiplied by square root of 1 square plus 1 square plus 1 square. This is the cos theta with the angle, cosine of the angle between 210 and 110. Now, the angle between these two is 2 into 1 plus 1 into 0 plus 1 into minus 1 divided by square root of 2 square plus 1 square plus 0 into square root of 1 square plus 0 plus minus 1 square into 3 MPa, and this will turn out to be 2 plus 1 3 divided by square root of 5 into square root of 3. This will turn out to be 1 divided by square root of 3, 5 into square root of 2 into 3 MPa. So, you can do the mathematics yourself. The stress will turn out to be about 1.4 to 1.5 megapascal. So, this will be the magnitude of shear stress that will act along 10 bar 1 direction when the stress applied normal to the face of the bar is 3 MPa. This can be worked out by doing transformation of axis just like we have done in this case. Okay. So, you can work out for any system equations like these and then determine what the stresses are going to be. Now, let us look at another example of related to principal stresses in principal stress calculation in a body which has been subjected to certain stress state. So, let us say we define sigma x is equal to 10 MPa, sigma y is equal to 8 MPa and sigma z is equal to minus 5 of MPa. So, we can calculate what is tau yz and tau zy. Tau yz and tau zy is given as minus of 4 MPa, tau zx is equal to tau xz which is given as minus of 4 MPa again. Sorry, this is let us see, the above is 5 MPa and then tau xy which is equal to tau yx which is equal to minus of 8 MPa. So, we can calculate what I1 is. I1 is, as we are saying, I1 is sigma x plus sigma y plus sigma z. Okay. If I1 is sigma x plus sigma y plus sigma z, then we can calculate this as 10 minus 10 plus 8 minus 5. This is equal to 13 MPa. Let us do the calculation for I2. I2 will be, as we wrote earlier, sigma yz square plus sigma zx square plus sigma xy square. So, we can replace this sigma with essentially tau, okay, minus of sigma y sigma z minus of sigma z sigma x minus of sigma x sigma. So, we have replaced the sigma yy with sigma y as the notation is. So, let us replace the values now here. So, this is 5 square plus minus 4 square plus minus of 8 square. This will be equal to and this is again sigma y and sigma z. So, this is equal to 5 minus 4 minus 8 and then this is going to be 10 into 8 minus of 8 into minus 5 minus of 10 into minus 5. Okay. And if we do the sum, this is equal to 115 MPa square. And I3 as we know is sigma x, sigma y, sigma z plus we can write tau yz, tau zx, tau xy minus of sigma x into tau yz square minus of sigma y into tau xy square minus of sigma z into tau y x z square. Okay. So, sigma x is, so we can say this is 10 into 8 into minus 5 plus 2 into 5 into minus 4 into minus 8 minus sigma x is 10 into tau yz is 5 square minus of sigma y, which is 8 into tau xz, which is minus 4 square minus of minus 5 into tau xy, which is minus 8 square. And if you do the maths, this will turn out to be minus of 138 MPa cube. Okay. So, now let us do the substitution. So, sigma p cube minus of I1, which is 13 into sigma p square minus of 115 sigma p plus 138 is equal to 0. So, this is I1, this is I2 and this is I3. Okay. So, basically this was the equation in which we have fitted the values, and if you solve this, above is sigma p values turn out to be 1.08 MPa, 18.7 MPa and minus 6.8. So, this is the solution you are going to obtain for the 3 principal stresses, that is sigma 1, sigma 2 and sigma 3. Okay. So, I hope it is clear from the formula that how does one determine the stresses sigma. So, now what we do is that, so having looked at the stresses in little detail, there is something which is also called as Morse stresses. If time permits, we will come to that later on, but now let us go back to the concept of strains. Okay. So, what we have worked out in stresses until now is basically what stresses are: true stress, engineering stress, what is stress tensor, the transformation of axis, and so true stress, engineering stress, stress tensor. We also looked at shear stresses, and we looked at transformation of axis, and then we looked at what is how do you work out the principal stresses. So, these are the few topics that we looked at under stress. Now, let us move on to the next topic, that is strain in the materials. So, if you consider a solid is being deformed, so let us say a very small strain, that is infinitesimally small strain, normal strain d epsilon is defined as a very small, let us say natural strain, okay, slash true strain is defined as d epsilon is equal to dl by L. So, this is the infinitesimal increase slash decrease in length. So, let us say if L naught is the initial length and LF is the final length, then this is from L naught to LF dl by L. So, it is integrated from L naught to LF and we get a strain which is ln of LF divided by L naught. This is called as true strain or natural strain. Okay. There is another strain which is, so let us say this is true strain. There is another strain which is called as engineering strain. which is given as E is equal to delta L divided by L naught, which is, that is, change in length or dimension with respect to original length. The problem is engineering strain is not a very accurate measure of real strain in the material, and there are a few differences. So, at very small strains these two values correspond with respect to each other, but when the values increase to large strains, then there is a loss of correspondence between the two values, and the reason is true strain is the spontaneous true strain, natural strain which gets added, which is equal in both tension and compression, whereas engineering strain has problems with respect to addition as well as when you calculate them with respect to tension and compression, as we will see later. Now let us see what is the relation between the two things. So relation between we can write this as LF minus L naught divided by L naught. So we write this epsilon as ln of LF divided by L naught. I can write this as LF minus L naught plus L naught divided by L naught, and this becomes E plus 1. So basically epsilon is equal to ln of 1 plus E as it is always, as it is expressed. So this is the relationship between true strain and engineering strain, and since epsilon is equal to ln of 1 plus E, if we do the series expansion, then we can write this as E minus E to E square divided by factorial 2 plus E cube by factorial 3 minus E4 by factorial 4 and so on and so forth. So we can see that as E tends to 0, epsilon tends to E, but this happens only at, which means at very very small strains. So let us do a little calculation. Okay. So we have a value of E, let us say we go from 0.001 to 0.0005 to 0.001 to 0.005, 01 to 0.05 to 0.1 to 0.5 to 1.0. Okay, these are the values of small e which are changing. So if we now calculate epsilon, which is ln 1 plus E, at 0.001 of strain, engineering strain, the value is 0.0000999, which is equal to 0.0001 equivalent, and if you calculate the ratio, this turns out to be 1.001. If you calculate for 0.0005, this turns out to be 0.0004999, and this is equivalent to 0.0005, and the ratio turns out to be 1.002. And if you do for this, this is 0.000999, and this turns out to be 0.001, ratio is nearly 1.002. Okay. And 0.005 will show you value of 0.00498, which is again sort of approximated to 0.005, and the ratio will increase to 1.004. And then you keep on doing this. When you come to, let us say 0.01, then the value that you get is 0.0098, and you can again approximate it to 0.001. 0.05 will give you a value of 0.0487, 0.1 will give you a value of 0.095, 0.5 will give you a value of 0.405, and 1 will give you a value of 0.693. and you can see this ratio. For example, if you calculate here, it will be 1.443, for this it will be 1.233, for this it will be 1.049, for this it will be 1.025, and for this it will be something like 1.01. So, you can see that these two values start diverging somewhere around 0.01. So, this is where you have sort of increased differences. So, it is only at small strains there is a good correspondence, but at large strains there are large differences. So, this is one major difference, that E and E have good correspondence only at very small strains. That is why true strain is a much better measure of strain than the engineering strain. What we are going to do in the next class now is we will take up more difference, we will understand more differences between the true strain and engineering strain, especially in terms of how do they add up and how are they related to tension and compression, as well as how are they related to volume change. So, what we have done in this class is we have looked at basically the principal stresses, how do you work out the principal stresses, and then how do you calculate the principal stresses in a slip. We just had a simple example of a tensile test in which a force is applied to normal to the faces, and then we calculate the stress on a plane on which slip occurs. We will come to the phenomena of slip later on, and then we also worked out what the magnitude of principal stresses. So, in the previous case we worked out the shear stress, and then we worked out the value of principal stresses once we know the value of principal and other normal and shear stresses. And then we looked at the conserved strain, the difference between true and engineering strain, and we will dwell upon it further in the next lecture. Thank you.